So here we are in the pops section, or the particles section. Really, this is going to be our introduction to dynamics in Houdini. While we're going to be building a particle system to sort of, expose the dynamic system to us, it's actually, there's going to be a lot of things about the way pops is set up, or particle operators, that is very similar to the way the rest of DOPS is set up. Originally, particles used to be in a separate section of Houdini called pops, but now it's all been integrated into the dynamics context. I find that particles generally tend to be like the most fundamental form of a simulation. I mean, basically you have positions of little points in space, and then you're applying a little bit of instructions as to how they should move, and then it's solving every single frame. And then the next frame will read the positions of the previous frame and then solve a little bit more and then push them along through space. And you can generate some pretty cool results with it. So what we're going to do to start off with, I'm going to switch to the quad view that I built in the intro to part 2. So I'm just going to go up here. And if you haven't made a quad view, please go check out that lesson, or you can follow along. But in whatever layout that you'd like. But for my purposes, I find that working in dynamics is really best when I have my quad view like this. So I've got my two linked network and parameter views here, and my geometry spreadsheet down here. I'm just going to hit the D key right here, switch my background to dark, and then under guides, I'm going to turn off my origin gnomon. So I got my nice black background the way I like it. Cool. So basically, let's just create a really generic particle system. I'm going to create a sphere, and then what I want to do is emit particles from this sphere. So I'm going to, like always, use the shelf tool as sort of a cheat sheet. And I find that this is super handy when you're getting started, and even if you need a little refresher as to how Houdini generally tends to set some things up. So I'm looking up here and I can see that there's this source particle emitter button. So I think what I'll do is try that one. And it gives me, you can see that what it does is it throws down these 3 nodes here, and it gives us a particle simulation. If I click play, you can see that that sphere is now emitting particles for us, which is great. I'm going to just hit the real-time toggle down here in the lower left-hand corner. So what has it done out here in our object network? It looks like it is, we created this sphere, but it's created 2 additional nodes for us. I generally like to stack these nodes that it creates when I've got a workflow like this, and I'll tell you why. Because it kind of represents the way data flows through Houdini anyways. When we're working out in SOPs, we generally build a network and it runs from top to bottom, and data is flowing from one node to the next. Now, even though these nodes aren't hooked up, there actually is a connection occurring between these two, because our sphere, which is created inside of here, is actually being pulled out and into this DOP network. And the DOP network is where the simulation of these particles is occurring. Then after that simulation is done, the particles are actually pulled out of the DOP network and back into another SOPs context inside of this source particles. So inside here, we've got our DOP IO, and it is fetching the particles out of our DOP network. Now, I find that this is sort of confusing because it's calling this by default source particles when actually we're sourcing our particles up here. So I'm going to just give this a name that makes more sense to me. And I'm going to call this import particles because we're actually taking particles out, we're importing particles from the DOP network back into SOPs. So let's see now, and it kind of achieves this by doing the type of object merge-like workflow that you would think, except these nodes are just a little bit different. Obviously, this DOP import node is not quite an object merge, but it's doing the same type of thing, just a slightly different interface. And likewise, inside the AutoDOP network that it created for us here, this is really our simulation. And we can see that we've got a source, and this source is pointing to our SOP and essentially merging in that SOP sphere so that we can emit particles from it. So let's look at this. This network here is sort of confusing at first, I think, for a lot of people. first off, we've got this pop object on the left, and then we have our source on the right. So if we're actually using this source to grab our particle source from back out in SOPs over here where our sphere is, then why do we need this pop object? Basically, the way dynamics works is we're taking an object, a container for a particle simulation, if you will, this pop object, and then we're attaching data to it. So that's really what this flow is as we move down our network here. So you can see we've got our pop object, and we're going to attach to it a pop solver. And basically, the pop solver is applying data to itself that allows it to really apply data to the pop object, which then feeds down our stream to our output. You can see that there's a merge here. We can use that to sort of combine other types of dynamics into our dynamic simulation. And then down here, there is a gravity node that just allows it to apply a force to cause these particles to fall down. So this merge really isn't needed as of right now, but if we wanted to put it to good use, we could throw down a ground plane so that these particles have something to collide with. So before I do that, I'm going to just hop in here, and I want to inside of our sphere, I just want to throw down a transform, and then bring our sphere up maybe, let's say, like 3 units in Y. So let's bring, I'm going to select the transform and say translate up by 3. So now it is above. And you can see down here, we had played back 24 frames, and now it turns orange. This orange means that it is that there is data cached in the RAM of our computer, but it is out of date. So if I actually go back to, and you can see that it's out of date because these particles are no longer where you would expect if our emitter was up here. So now if I go back to frame 0 and hit play, you can see that it's emitting from up here now, and then we get this nice blue bar. That basically means that we have a current and up-to-date cache in our timeline. So with that out of the way, the next thing I want to do is just talk about how the data is flowing through this dynamics network by adding a ground plane. So we're just going to be adding another dynamics object to get involved with our system up here. So I'm going to go up to the collisions tab on my shelf up here. I'm going to click ground plane. You can see that it throws in a static solver for us and a ground plane over here. I'm just going to hit the L key to lay this out. And you can see that the ground plane is going into its own merge. So if I wanted to merge in other static objects to collide with our geometry, I could do that here. And then it goes into a static solver. And truth be told, the static solver actually doesn't really do anything. It's actually more or less here for us to feel comfortable about using and applying a solver to our static objects. When in fact, if we look at this merge node here, this merge is creating for us a collide relationship, and it's creating a mutual collision. Because of the fact that our ground plane is actually a static object and it will never be affected by our sphere, our particles rather, there really is no mutual effect happening here. So what I could just choose is left inputs affect right inputs, and that basically will make it so that the ground plane only influences the popnet. So really that's what this merge is actually doing, is it's establishing that collision relationship between these two dynamics objects. So actually I don't really even need those nodes, so I'm just going to delete them. And if you check it out, if I rewind back to 0 and click play, you can see that those particles now, they hit the ground plane and then they just sort of bounce, and then they kind of start sliding off into nowhere. So that's like sort of the basis of how you can create your own kind of collision object. Now, if I go up here, I mean, as far as a ground plane is concerned, if we wanted to add more colliders to this system, we could do so. For example, if I wanted it to collide with another plane, I could add another sloped plane in here. So if we look over here out in our object context, you can see that it created this ground plane object for us. This is simply the geometry that we're seeing here in our scene that represents a ground plane. So we can create that using the shelf. The other thing we could do is I could actually manually go and create some collision geometry. I'm going to just do that by throwing down a grid, and I'll hop into the grid. and I will use a transform. And I'm just going to bring this grid up a little bit, and we'll rotate it a little bit just to give it a little bit of a slope. And maybe I will just bring this back slightly so it has a little bit, so that it can slide off the edge of this pretty quickly. So now if I wanted to turn this into a collision object, I could do that using this static object. So because a static object versus a dynamics object, a dynamic object is one that is really moving and is affected by things that are both not moving and moving. And a static object is simply, it sits still and affects the dynamics network, but really isn't actually being pushed around by it in any way. So that's what we want. We want this grid to stay still, and we just want to bounce these particles off of it. So I'm just going to click with my grid selected out here in the object level. I'm just going to select just static object. And you can see it's done the same thing for us again here. It's added another merge for us, and it's added a grid and another merge and another static solver. This is a little bit extreme. I don't necessarily need the static solver anymore. I don't need this merge either. So I'm just going to delete these two. Or actually, I'm going to keep, I'm going to delete these two. And I'm just going to keep this merge around. I'm going to wire this back in here where it was. I'm going to wire this down here now and just merge these two colliders together. Now, because these both are static objects, they really aren't going to have any effect on the scene. So, or they're not going to have any effect on one another, but we still merge them in before we merge them into our simulation over here. So really what happens is when we're doing a merge, we're bringing in things, and it's really kind of reading everything in the network from the top to the bottom, but it's also going from left to right. So objects that are flowing in from the left are affecting objects that are coming in from the right. And then once they're merged, then we apply gravity to everything, which obviously it isn't going to affect these objects because they are static. So now if I were to rewind this, you can see that our grid pops up. And if I click play, these particles are now kind of passing through this grid. And that's going to be because some of the default settings, there are many different collision types in our dynamics context. And if I go over here and I look at this, it's using a volume sample to set up the collision. And in our case, because this is just a grid, we really don't have any volume to sample. So I'm going to switch this over to using surface collisions. And so if I hop over here to my surface, I've got my volume collisions and my surface-based collisions. If I switch over to my surface-based collisions and say show collision radius, you can see that this green guide shows up for us, just to represent where our collisions are going to occur. So I can turn that off. I don't need to see that. But now if I rewind and click play, those particles are bouncing off the grid. So as you go through your journey in learning Houdini, you'll start to get familiar with what types of simulations work best with what types of collision geometry types, as well as what types of collision geometry types to use depending on what type of input geometry you have. So in this case, this is working fine. And I just wanted to sort of go over how you can create collision geometry. So now let's look at some more of the sort of features of these sourcing and this pop network that we're creating here. I'm going to just, for the time being, I'm going to just turn these two off. We've got display flags similar to how we do up in SOPs. So if I go up here to this downward arrow, click that, I can bypass those two nodes. Our cache turns orange, and we still see the objects in our scene, but if I rewind it, it resets the simulation, and we only see the ghosted objects out from our object level. So if I actually go up here and turn on hide other objects, you can see that they really aren't in our dynamics network anymore. And now we're back to really where we started from. That's sort of what these bypass flags do. Additionally, there is this orange flag down here, which represents the output. So what I could do is, for example, if I set my output up here, you would see that if I click play, now gravity is not affecting the system because it's only outputting where this merge is occurring. So that's just an important thing to note about, just an important thing to note about the flag system inside of Dynamics. That's really what that output is. Generally, I keep it set to this output flag at the very end, pretty much at all times, unless I'm trying to, figure out something, if something's broken or whatever. So let's look at some of the birthing features over here. You can see that our source is set to grab this SOP sphere that's right here. Now it's grabbing if you look at the path, it's grabbing object and then it's grabbing sphere 1. That means that it's actually grabbing this top level of geometry. We very well could go in here and create a null and point it to that null and have this be the actual source. So I could say source. Now, a strange thing to note about the way that SOPs work is obviously I've got my sphere here. If I were to go in here and just set my display flag to this actual sphere 1 up here and go up to my sphere object, you can see that it's actually representing my geometry back at world origin, even though I have done this transformation inside of our network like this. And it's important to note that because if you're in here trying to modify your geometry, sometimes you'll forget to set your display flag to, this, to the end of your chain, and then you'll hop back into your Dynamics network, and then you are back to emitting from a location or a portion of your network that is unexpected, that you weren't trying to have it emit from. So one thing that you can do is, and this is one thing I actually like to do, is explicitly tell sphere 1 source to actually pick a null to emit from instead of actually emitting from this top level here. So if I actually go in here and I grab my source null like this, I can actually drag it over and drop it right in there. You can see that it creates a relative reference for us. And then if I go back to 0 and hit play, oops. If I go back to 0 and hit play, sorry, something weird happened. I had to kind of just click a couple nodes. Sometimes weird things like that happen, but you click back and forth a couple times and it sometimes debugs itself. But now you can see that I'm hitting play and it is emitting from the end of my chain here, even though I haven't set the display flag there, because it's specifically set to emit from this particular SOP that I've set here. So just in case things are starting to get weird like this, my sphere is actually displaying sphere 1 at like where it was created at the origin, but I'm emitting from up here. Just an important distinction to make, that things can get a little bit tricky like that, but I prefer to be as explicit as I can, because now I can go up here and start adding things in here and changing things, and suppose I only have this highlighted, or I'm still working on the sphere, it will still update at the bottom of this procedural chain that we're creating and use that in our sim. So what are some other features up here? You can see, if I go back to 0, you see we get this nice kind of blue outline of this, of our geometry. And I'm going to go over here to our sphere and actually change this to a polygon and increase the frequency to make it a little bit more obvious. Now when I jump back over here, you can see that it's creating an outline of our emitter geometry. That's this guide up here. That's what this is for. So if I turn this on and off, you can see that it will represent our guide for us. If I turn it off, it'll still emit, but we just won't see that blue outline anymore. So other emission types here, we've got scatter onto surfaces. Basically what that means is if the geo that this is seeing is actually a surface, a piece of geo, just like this, where we've got polygons, it's going to, on its own, just randomly scatter points all over the surface. The way it's going to do that is it's going to use this constant activation rate. Now, the constant activation is set to 1, and the constant birth rate is set to 5,000. That basically means that it will spawn 5,000 particles per second. So if I scroll out here to frame 24, and down here in my geometry spreadsheet, if I go to open this pop object, and I scroll down to my geometry right here, and I click on it, you can see that I get many of my attributes that we were, a lot more attributes than we've really dealt with up until this point, but this is sort of like the geometry spreadsheet that we're used to seeing out in SOPs. Now, if you if I were to look over here, I've got this point number. If I sort by point number, you can see I've got about 5,000 points. That makes sense. And as I continue on, that number increases up to, you know, whatever 5,000 times however many seconds are on, you know, so 48 frames, 2 seconds, 10,000 particles. So that's what this birth rate means right here. Now, if I were if I go back over here to my source and I say, and I choose a different scattering option, I could choose maybe scatter from all points. And if I turn the guide on, and maybe I'll just go up here and turn this frequency down just to make it a little bit more obvious. But if I go back in here, you can see that we're actually emitting 1 point from every intersection wherever there is actually we're emitting a particle from every point of the geometry, and it doesn't move around. So it's actually staying pretty much, those particles are all emitting from just these locations that we're explicitly defining for it, which can be handy if you want to supply your own sort of emission pattern over here. So for example, if I wanted to say scatter, I could, for example, I could scatter my own particles across this geometry. I'm just going to increase the frequency to make it a little bit higher res. But then I could also do something like, I could paint in some density. So I'm going to go over here. I'm going to throw down a paint node. And if I just wanted to emit from like certain parts of this sphere, I could paint in those areas. So I'm going to just go my background. I'm going to apply to all. So I'm basically went to this background color tab. It's set to black. I'm applying that to all. That's cool. And then in the foreground color, I'm going to just set that to white, and then I can paint. I'm just going to middle mouse this mouse button a little bit bigger. I'm just going to paint a little chunk here and maybe a little chunk here and maybe a line like that. So we've got a very just a couple little areas on our sphere that we can choose to drive our density in our scatter. So if I go down to the scatter now, you can see that color is being picked up. But if I show my points, that they're all distributed evenly. So now what I could do is set a density attribute, and because the density attribute doesn't exist, I could just choose color, and we'll delete density out of that field. And now you can see that it is clustering those points right around where we painted in that density. So now if I jump back over to my PopNet, and I'm going to turn off this point, these point guides here. I'm just going to rewind this, and you can see that now that we have selected from our sphere source to use all points of this source null, it's only going to emit from those sections that we painted out. Like so. So now if I go over to the birth section, you can see that it's actually using this impulse activation. This impulse activation basically means that what we're going to do is every single frame or impulse, we're going to emit from literally every single point that we're receiving. So because this scatter is set to 1,000 points, and it's giving us 1,000 points every single frame, by the time we get to frame 24, we should have 24,000 points in our simulation. So if I go over here on frame 24 and I sort by points, you can see we've got 23,999, close enough to 24,000 points. So that's just one way that emitting from all points is different from scatter onto surfaces. Is that we get this impulse activation, and we can actually, you know, if we wanted to turn this off, we could. If we only wanted to emit for a little while, we could key this and then just go to the next frame, like frame 25, turn it off, and just if I zoom out a little bit, go back, hit play, impulse is on, and then it turns off. Cool. So that's one of the ways that, another way that I find to be quite handy sometimes when I'm trying to emit particles in a certain format. It's just a nice distinction to be able to make those two different settings. And basically, if you really wanted to, you could actually leave this set to all points and just explicitly set up your scatters every single time and get very similar results as you would get if you were just using scatter onto surfaces. Points in general operates in a pretty similar way to the scatter onto geometry. It's just that what it will do is actually use this constant activation parameter again. So now we could actually explicitly say, well, I want you to emit from points, but I only want you to emit, say 25 or sorry, 24 particles per frame. And that way we would get one particle being emitted every single frame into our sim. And it would be choosing one of these particles from our lineup that we've supplied it here. So if you see, if I click play, we're just getting very few particles, but they are all emitting from one of these points that we're defining right here. Cool. So with that, I'm going to just switch this back to our scatter onto surfaces option, and it's not going to really know what to do because we're not supplying it a surface. So if I hit play, nothing happens. And what I could do is just mute these two options so that we just get actual surface back, and go in here and click play, and there it is, emitting onto our, or scattering onto our surface back at these settings that I left it at, which is 24 frames a second. I'm just going to turn this back to 5,000. So we're pretty much back at default now. So if I click play, you can see that it is just emitting a whole bunch of points, as 5,000 per second to be exact. So another thing over here we can do with our emission is we can give our particles a life expectancy. So by default, they're set to live for 100 seconds, which is pretty much longer than probably most simulations you're going to want to do. But I could, for the sake of demonstration, just set the life expectancy to 1. So now our particles will only live for 1 second, and then you can see that after 1 second of life, they go down here and then they just die away. Another cool, and this can be super handy if you're trying to do fireworks or sparklers or something like that. It's great. And another cool sort of parameter that goes into that is the life variance. So if I have a life expectancy of 1 second and I give it a life variance of 1, then that's sort of adding a plus or minus range onto our life expectancy. Basically what we're saying now is that our particles can live 1 second and anywhere in between -1 and +1 of that value with this life variance. So really all these particles could live from anywhere from 0 seconds all the way up to 2 seconds. So now the stream should get longer, but it should also be thicker towards the top and thinner towards the bottom. So if I go back and play this, you can see that certainly it plays a little bit longer and it's thicker towards the top, but it starts to peter off towards the bottom as those randomly determined ages are finally being killed as they reach their maximum here. So that's one thing to note about adding some life variance into your simulation if that's what you're after. And I think it actually ends up looking a little bit more random. So if I, for example, wanted this to live to be only 1 second at maximum, I could make my life expectancy 0.5 and change my life variance to 0.5. And so now really we're kind of where we were when we had this life expectancy set to 1 and our life variance set to 0. You can see that it's all of our particles are coming down here and then immediately stopping. But what if I add that variance in here and set this to 0.5 and 0.5, it's the same, but it just has like a more gradual die off. So just a cool thing about life variance and life expectancy in pops. So now what I want to talk about is these attributes over here. So you can, if you notice, we've got this sort of, if I just turn off gravity for 1 second, I'm just going to mute gravity here. So gravity is having no effect on our simulation. I'm going to go back to frame 1 and click play, and you can see that all of our particles are sort of spawning and flying away and dying randomly. And that's because we have our attributes here set to add to inherited velocity. Now, if I go over here, inherited velocity, what is that? That would be if we were to set velocity over here in SOPs using like some attribute randomized field maybe, we could actually take that velocity into our PopNet and use it to drive the initial launch of our particles. So if I middle mouse click here, you can see the only attribute we have is position. That's the only attribute that's coming into our DOP network over here. But So if I turn off, if I turn this to use inherited velocity instead of add to inherited velocity, you'll see that since there is no velocity to inherit, these particles are just birthing and dying on the surface of this sphere. I'm going to just increase the life variance a little bit on this real quick. Just going to go back to birth. Increase the life expectancy to like maybe 5 and the life variance to 2.5. So now the particles live just a little bit longer. So back over here on attributes. Now, if I'm adding to the inherited velocity, you can see that there's some variance that it's applying to that velocity that it is inheriting, which is nothing. So if I actually click play, you can see that these are all flying off in random directions. If I turn this variance down to 0, like so, now we are sort of back to where we were in the first place. Now I could add some velocity to this if I wanted to. I could explicitly say I want this to go, I want this to go have a velocity vector initially pointing 4 in the x-axis, and you can see that now it's just launching these particles off to the left. And without gravity, it just looks kind of funny. I mean, they're just kind of going out there and dying, and it's pretty boring. But now when you start mixing these forces and velocities back together, you start to get more interesting results. So now this is sort of like behaving almost like a stream. And then if I start to introduce some variance back into it, you can see that we get ever more erratic behavior. Cool. So this is really one way, just one of the features built in on the pop source, that we can use the pop source to manipulate sort of our velocities in the dynamics context. But what I think is even more powerful and somewhat more handy in most situations is to actually be able to set velocities and inherit velocities as one example of one type of attribute you could inherit from SOPs. So let's actually show how that works. I'm going to go back here and I'm going to just say use inherited velocity. So as we were before, this is obviously going to do nothing to our particles. I'm just going to turn gravity off. It's going to do nothing to our particles because we have no inherited velocity, but we can set up a velocity attribute over here in pops. So let's do that. I'm just going to throw down a attribute noise. So I'm just going to wire this in right before our source. And you can see that by default, it's setting a random noise to our color attribute, which is kind of hard to see. Let's just highlight this. You can see this kind of rainbowy color as it's creating random color vectors for us. Since that's not what we're after, we want to use the universal velocity attribute that sort of comes with Houdini, and we hit the V key instead to put a V in for our attributes. So now this goes away, but we get a velocity attribute down here in our geometry spreadsheet. And then if I go over here and click trail, this velocity trails, you can see that it's kind of hard to see, but if I turn on wireframe, now it's kind of, there are these little tiny green arrows that are sticking away, that are pointing away from our points. I'm just going to make these a little bit more obvious by hitting the D key, going to my guides, and I'm going to scale my vectors up to 10. So now you can see that it is creating these velocity vectors, and these are sort of trailing in the direction of our velocity. So if I switch back over to pops now, I should have, based off of what these tails are doing, these particles should be launching off to the upper left of the screen, which they are. You can see that they're kind of taking on a slightly random trajectory as this noise pattern isn't completely uniform. It's actually got a little bit of noisiness to it if we look at this. So not all these vectors are pointing in the same direction. So we can now vary this. I think that because we're doing additive mode, we basically we're just adding velocity to a velocity that doesn't exist. If we switch to multiplicative mode, I think that it doesn't look like it really changes anything. I'll just leave this at additive for right now, but if I choose now, because this noise is being added to a velocity that is based at 0, you can see all of our velocities are ranging between 0 and 1. And that's cool if that's what you're after, but really I want this velocity to vary in all directions. So I want some velocities going in negative x direction, positive z direction, negative and positive y directions. I want it to go everywhere. So cool way to get that done in the attribute noise is to just tick this center noise option. And you can see that it is that all these trails have sort of some of them have disappeared, but that's because they're pointing outward from the inside of this sphere. So if I dive inside, you can see that some of these vectors are pointing away, some of them are pointing in. Now if I hop over here to our PopNet and click play, you can see that those velocity vectors it's pointing in all sorts of crazy directions, which is cool. And then if I wanted to, I could animate this. So every time particles were spawned, you could see now these velocity trails are changing direction. I want to see if I can, I'm going to hit the D key one more time and scale the vectors up to some really large number, like, like 70, just so that I can see them more obviously. Obviously this is a visualizer, so it's not having any effect on the sim. It's just making it easier for me to see these velocities. And if I go back over here, you can see that now with that animated velocity, it's sending particles out in all sorts of different directions. I'm just going to turn off the trail, and then maybe just to mix things up a little bit, we could modify the. Sorry. I'm going to go back here and grab our pop object right here, and then I'm just going to pin this view so that when I'm over here working in my SOPs context, I'm not going to lose the dynamics. I'm not going to be able to, I'm going to still be able to see my dynamics network over here. So now that I'm over here, I could change this, I could change the element size to be, a little bit, I'm going to turn off animated for a second, and I could just change the element size to be a lot smaller. And now it's generating even more tightly wound random emission from these velocities that it's inheriting. So now if I were to, maybe turn on gravity and see this all play out, it looks like it isn't having too much of an effect here. So I could go and increase the magnitude or the amplitude of this random amount over here in SOPs. And you can see that that's having an effect on our sim, like so. And also I could just maybe change the element size. So the larger I go, the more randomly distributed that the noise, the velocities are. And if I switch this back onto animated, you start to get them whipping out in all sorts of different directions as it changes that noise pattern that is flowing through our particle system, or our emitter rather. So those are some fun things that you can do to inherit velocity into your system. If I bring this amplitude down now back to something like, I think it was at 1, I'm just going to set back to 1. You can see it's having very little effect on our simulation. If I go back over here to our emitter, you see that there's this inherit velocity as well right here, and there's a slider. So I can actually tell this explicitly on the DOP side that I want to multiply it by 20 or something, wherever I had it before. And now we're getting the same result. This is basically like if I were to multiply this amplitude by 20, except now I'm just controlling it over here. So if you're working in different contexts, sometimes it's really handy to have most of your control over here, or maybe you want to have most of it over here. It's just nice to know that if you're, multiplying and changing your amplitudes over here, you might need to tweak them more over here, or if you're not getting an expected result. I know that it might seem confusing to have these settings in two places, but really, ultimately, I think it's just designed to be more user-friendly so you don't have to hop back and forth between SOPs and POPs quite so often. All right, so let's talk about what other forces we can add into our dynamics network at this point. Basically, it looks like we're actually applying force to this, that is this random noise, but really what that is it's a force that's being generated at birth, and then it is more or less only being modified by the acceleration of gravity, which you can see here is set to negative 9.8 for negative, real world units were in meters, and this would be negative 9.8 meters per second squared, or the acceleration of gravity as it would be in the real world. What other forces can we apply to this? just to make things a little bit more obvious as to what we're doing, I'm going to actually turn off this inherited velocity. I could turn it off here. I could go over here to our sphere source and say, I could dial this inherited velocity all the way down to 0. So if we want it back, we can just do that or not, whatever's good. I'm also going to turn off gravity just to make it obvious what's going on. We're just having particles right here. So if they're just birthing and sitting literally on the surface of the sphere. So if I apply any forces, we'll know that they're doing something. A lot of times I'll do this kind of workflow. I'll start turning things off and making sure that I have sort of like a controlled situation so I can see just exactly what my particles or my forces are doing. And then I'll just gradually add back in all my other forces in my scene. So to add a force, what I could do is I could add a, let's check this out. I'm going to hit the tab key in our dynamics area. And you can see I've got all these different types of nodes that are really specific to dynamics. This isn't the type of things that would show up in our SOPs context. This is, we've got things for finite elements. We've got forces. We've got micro solvers. These are all sorts of crazy little solvers that allow you to do gnarly things. And then we've got pops, and these are specific, these are the old school particle operators that now really kind of work with many more parts of the dynamics context as well. So it's kind of interesting. We've got this force thing. So for example, we've got a gravity force here, which is what this node is right here. Now, if I go over to my pops section, I can also create a force here as well. And where I wire this in, I usually like to wire it in over here by my pop source. So I've got my particles that are being emitted, and then I just want to apply a force to them. So I'm just going to wire this in here. You can see that nothing happens by default, but if I were to type in negative 9.8 here, we would get a similar situation. It looks like we've added gravity. So really there are basically two ways of accomplishing the same thing. Now pops and this general regular DOPS force right here, not all pops force will work in every situation. For example, if we wanted to add gravity to a smoke simulation, smokes are not really particle based. They're more voxel based. And so gravity will work on those. If it's a DOP gravity down here, pop force won't necessarily work on a volume. So it's just important to note. I find that whenever I have the opportunity to work with pops, I just find pops to be, I mean, maybe it's just me, but I feel like they're a little bit faster and just a little bit more user friendly. But you can use these pops to modify your particle network. So we've got this pop force, and we're making it act like gravity for us right here. Other things we could do is one of the cool features that's kind of hidden on the pop force node is a noise. So I'm actually going to turn this this constant force, this directional force off. I'm going to go back to frame 1 and play, and it's not doing anything. But now if I start cranking up this amplitude, you can see that it starts adding this crazy turbulence to our particle sim. And now we've got all these parameters that we can mess around with. Swirl size, basically the swirl size is the frequency. So a larger swirl size and the lower frequency of an undulation it will create on our particle system. Also pulse length. The pulse length is a pulse length of 1. The longer the pulse length, that means like the longer it will take for this noise to evolve in our particle system. So if I actually bring this pulse length down, you can see that the noise is going to shift. It should start shifting faster and faster. So let me bring this way down. And it looks like it isn't having, it looks like it's actually shifting so fast that it's barely moving our particles because they're being kind of jostled back and forth so frequently. So if I increase this amplitude a bit, you can kind of see how that pulse length is moving things much faster now. So if I bring this pulse length down to something like 3, we'll get like obviously very aggressive pushes in certain directions, but it'll take it a while for it to change which direction it's actually applying that push. So I'm just going to bring this amplitude back down to something like 2. Should be good. So yeah, we're getting this nice kind of random swirly behavior being applied to our particles. And then you've got other controls like roughness. You can bring the roughness down. You can mess with your different turbulence. And basically, these settings just add more or less detail and chunkiness to the turbulence as you're messing around with your as it affects your system. So that is really the pop force node. Another cool node that I want to show off is the curve force. So I'm going to throw it on a pop curve force. And because we aren't using our collisions on the ground anymore, I think what I might do is actually turn off this transform as well, just so that we're dealing with the ground, so that when I'm building my curve, I can actually I don't have to move it in space to match up with my sim or anything like that. So I'm gonna so this pop curve force, I'm just gonna wire this in now. And now our pop force isn't really, let's see, is our pop force still doing something? Yeah, our pop force is still doing stuff. I'm just going to bypass it for right now. And I'm going to hop back out here to our geometry level. And I'm just going to create another geo. And call it curve. I'm just going to dive inside here, and then I'm going to create a curve node. Curve, like so. And then what I'm going to do is hit spacebar 2 to switch into my top view. And then I'm just going to draw a curve. Now I have my curve right here. There are no coordinates that are initialized in it already. If there are, you can delete those. But I've got my manipulator selected here, and so I can just start. Can I start? Oh, no. I can't start drawing because I still have my view pinned up here. So I'm just going to unpin it. And now I get my nice little kind of marquee tool, and I can start drawing my curve. So I'm just going to do something like a spiral like so, and I'll hit enter. Then I'm going to hit spacebar 1 to get back into my side view. I'm just going to, with this manipulator still selected, I'm just going to kind of manipulate these points to kind of maybe spiral upwards like so. So I'm just going to grab this one, bring it up. Maybe what I'll do is I'll switch into my 4 views and go over here to the side views, frame these all up. And I'll select maybe this one, and we'll bring it up. And this one up a little bit. Yeah, we'll bring this guy up a little bit more. Just really trying to create a spiral. This will be a lot easier to see if I turn this into a NURBS. So now I'm getting sort of like this kind of corkscrewy look. I'll grab this guy and bring it up. Yeah, maybe this one can swoop down a little bit. Whatever suits your fancy. Just any old curve will do. So yeah, I'll just go with something like this. And so now that I have this curve, what I can do is source this curve in as our SOP path. So it's this pop curve force is looking for a curve. Let's drag this in here. And you can see that it creates this kind of guide geometry for us. I'm going to switch back to single view. Now you can see that this guide that it creates is sort of representing the field that it is going to be applying to our particles. So now I have no other forces applied. If I click play, you can see that it starts to send these particles flowing along that curve that we created. Just to make it a little bit more obvious, I'm going to hop up here. I'm just going to turn off this particle import. I'm going to turn off the sphere as well, but I'm going to leave the curve visible. And then I'm going to go in here to the DOPNet. And if I turn on up here, show all objects, we can kind of see that curve flowing through the center of our thing, just so that we can kind of see what's going on with it. So let's look at some of these parameters on this pop curve force. Now I see these gigantic lines that are flowing around. Really what that means is I think it's really just representative of the maximum influence radius. So how far away from this curve particles can be affected by it. So if I bring this down, you can see that gets much more narrow. And then if I were to hit play on this, you can see only a few particles are being affected and pulled in by this. And then honestly, they're being pulled by it, and there aren't enough forces on this curve to keep those particles attracted to the center of the curve. So they just fly off into space like so. So, you can dial in settings like this, and, get it to do its thing. Now, if I were to say I want to get all these particles back in business, but I don't want any of them to fly away, there's also this suction scale force. Now, if I start cranking up the suction scale above 1, you can see that it's really doing a better job of keeping these particles that started inside of this curve radius to continue following it. And likewise, they're all spinning around. That's what this orbit scale is. So if I turn the orbit scale down, not to -1, just to 0, you can see that it's really just sucking particles in and pushing them along the curve. And now if I increase the follow scale, they should move a little bit faster. And you can see that now, because that follow scale, as it pushes those particles along the curve, because that follow scale is so hard, the suction scale is not powerful enough to keep it within that force. So you could start messing around with increasing the suction scale and eventually getting it to a point where it sends these particles all the way along this curve and then spits them out the end here, where it's got this green arrow indicating that it's just going to send these particles flying off into wherever. So yeah, if I were to actually increase this max influence radius so that it encapsulates this entire sphere, we can actually have it suck up all of those particles and send them flying along like so. And maybe we'll add just a little bit more orbit force in there, see if it makes things a little bit interesting. Things are moving so fast that it's kind of hard to tell at this point, but I'm going to maybe bring this follow scale down a little bit. And you can see that the orbit scale is doing something funny now. I'm just going to bring this back a little bit so it's not orbiting so intensely. You can see that it's sort of just getting sucked and then eventually stopping. I think that's because this suction scale is so intense that it doesn't actually have the opportunity to continue along the curve. So I'm going to bring this follow scale up a little bit more. And there you can see we get this this stream of particles kind of following and being sucked inward along this curve. Now, we could change this influence radius along the radius, now along the length of the curve. So if we go down here, you see that there's all these fall-offs. So like if I go to global forces, let me see, force along length. So yeah, here we can like adjust how much this is actually affecting it so that by the time it gets to the end, these forces are not having as much of an influence. So you get all these really handy ramps for guiding particles around like so. This global force fall off from curve, let me see if I modify this might make it so that this would be it would represent like the further you get away, you can modify how much of an effect it's having on your particles. And here you can scale the influence radius along the length, and you can kind of see that kind of falling. We can see it's actually tapering as we get to the end of this curve, which is kind of cool. So now, like now that we've done this, we could actually this is pretty basic looking simulation, even though it's kind of doing something fun. We're guiding these curves along. This is where you start combining things together. We could actually add back in our turbulence and give it some more amplitude so that really this kind of like has sort of like an interesting undulation as it moves along our curve. Or we could do a, let's see, if I maybe bring this swirl size down a little bit, just try and mix these forces together so that you can add, different kind of interesting behaviors to your curves. Now I see that like all these particles are starting to fall off at the end, which is fine. But this is really where you could kind of mess around with keeping your global forces strong along the length of your object. That way they're sort of staying, they're staying and doing what they're supposed to do. Just gonna go back here. So now, now there's this. I could also add some more interesting behavior to it by maybe reintroducing the inherited velocity that we had before. So if I bring that inherent velocity in, it's not having too much of an effect right now, but if I bring it up quite high, you can see that there's that initial velocity is sort of launching some particles out. Some of them are sticking along the curve. And so really it's just a playground. Anything you can think of to try and combine these to get cool things to happen. Now, another way I like to kind of keep things under control is there's other nodes. So if we go in here and look at our pops, we've got pop attract. I think is pretty fun. We've got the pop axis force. I'm just going to throw a pop axis force down here, and let's just I'm going to turn these two off. So we should just get really crazy. Now what we get is just our inherited velocities launching these all over the place. I'm just going to bring the inherited velocity back down to 0. We got 0 here. And our pop axis force. Now this is like another type of force that we can use to like do other types of vortexy type things. So you can see if I increase the radius like so and click play, you can see that all these particles, they kind of start orbiting around this object in this sort of shape. And so here I can we can change the orbit speed to orbit faster, and we can increase the suction speed so that things don't quite want to escape. So you can do that. Kind of do that delicate balance of trying to maybe create a galaxy or something like that. I've had much fun trying to create galaxy systems using this, and maybe adding some of that turbulence back in, and using them all together. So you've got your orbit speed, how much it's orbiting around, your lift speed. I think we'll push it just vertically. Yeah. Looks like the lift speed actually pushes these particles up in space, and then your suction speed actually brings them in a little bit. So if I bring this shape height up, and I'm just going to turn the lift speed down to 0. You see you kind of get this like orbiting thing inside of it. Let's just bring the suction speed down a little bit. You can really see that you're kind of getting that, you get that play between your pop force, the turbulence that you created, and this orbiting force that's occurring on this pop axis. Very fun. So you can also change strengths, inner strength, outer strength. So now it's going to just continue to have the same strength outside the sphere as it does inside the sphere. I could change, maybe bring this suction speed down a little bit and dial it up. And this is what a lot of sims are, is just balancing and having fun and playing around with things and whatnot. So now, like, I don't even know what would happen if I add the pop curve force in here. Yeah, you can see the pop curve force actually just is so powerful. It's taking over, but yeah, it's kind of combining with it and creating this weird spirograph type thing. So those are just some of my favorite forces in pops. One other thing I wanted to talk about real quick before we get into moving on to other parts is the pop grains. So I'm going to switch all these forces off, and I'm going to just go back to frame 0. I'm going to go back into my sphere over here. I'm going to turn back on the transform, and the reason why is because I want to just quickly show what the old grains are. Now we've got vellum grains, which is part of the new vellum setup. Those grains are amazing as well, but there's also a pretty simple way of setting up grains just in the context of this pop net that we're already working in, and I just wanted to show that off. So I want these grains to fall and collide with the ground, so I'm just going to turn the ground plane back on, and we're just going to throw it on a pop grain. And pop grains basically allows the particles to collide with one another. So if I click play, I'm getting a little warning here on the pop grains. So if I look at that warning, it's saying it's requiring the p-scale attribute. The reason why grains require the p-scale attribute is because it needs to know what radius away from the center of the particle it needs to compute the collision with a neighboring particle. So I'm going to go over here, and in our let's see, our SOPS sphere emitter here, I can add a p-scale attribute. So I'm just going to create an attribute. Using an attribute create, I'm going to call it p-scale. And I'm going to give it a value of like 0.1 for right now. I'm just going to off to the side here because I don't want this to go into my source. So I'm going to put down a sprite just so I can get a view of how big the p-scale actually the p-scale attribute actually is. And I'm not seeing anything because I should scatter. So I'm just going to scatter onto my sphere. It's not going to work because I don't have density because I have this paint turned off. So I'm just going to untick density. And now when I go down here and turn on these sprites, you can see that I get these little smoke puffs that are in the size of that are roughly representing the size of my spheres. I'm going to just change from smoke puff. I'm going to go over to my Houdini pick texture and then jump up one folder. And then I'm going to go down here to sphere and I choose sphere deep and hit accept. And sometimes this doesn't update right away. I have to go back to frame 0. Now I can get an idea of how big my p-scale values are. So, I mean, that's looking fine for right now. It's maybe a little bit big. I'll maybe just dial this back a little bit and see I get that visual representation of how big my particles are by setting them this way and just using this sprite as a reference. Now over here in Pops, Pop Grains is happy now that it has a that we've provided it with a p-scale attribute, but I am still scattering, so I don't have this I don't have the scatter. I still have scatter onto surfaces selected, so maybe at this point just I'll switch it to all points. So now it's going to scatter those spheres onto these points that we've scattered right here. And if I click play, you can see that it creates this, that all these points just start blasting off in all directions. Another thing that I want to do, I think that we're actually scattering quite a few too many points. So I'm going to actually turn the scatter off and then choose scatter onto surfaces here so that I can kind of control this birth rate from within Pop. So I'm going to just set the birth rate down to 100, something a little bit low. And then I really can't see what's going on with this. So I want to actually throw down a similar thing like what we did over here with the sprite. I'm just going to throw down a Pop sprite. Pop sprite basically just allows you to view a sprite representation in your simulation. I find it to be kind of handy when I'm doing stuff with grains, especially because I want to see the scale of my grains colliding with one another. So again, I'm gonna just copy what I put over here. It's just HFS Houdini pick sphere deep pick. I'm just gonna copy this. I'm just gonna paste it in here under that section and hit enter. And if I go back to frame 0, it might not update right away, but there you go. I'm starting to get my little spheres in there just to help me visualize. So now without any gravity, this isn't really going to collide with our ground floor. So I'm going to turn gravity on. And I think actually at this point, I'm going to increase my P scale back to 0.1. And now over here, you can see I'm dropping my, my particles on the ground and they're colliding with one another like little grains of sand. Cool. So really, it's kind of interesting. This grains node sort of has its own little solver within it. You can see that it's got these. It has all these behaviors with how it behaves in terms of its friction and constraints and clumping and all this stuff. You can simulate wet sand using this as well, and you could even simulate cloth using this. But we're not going to do that because we're going to be doing cloth and vellum, which is way more fun. But it's cool. It's almost like a little tiny solver. So really what we're doing is we're attaching more data to our particle source, and then we're applying that data to our pop solver, which is applying it to our pop object, and then flowing through with all the rest of the elements in our adopt network, such as colliding with the floor and whatnot. So what else can we do with this? I want to see if I can really get this to start piling up into a stack. So I'm going to just hop over to the pop grains and I'm going to increase the constraint iterations. Constraints really in terms of PBD sims are really kind of referring to sort of how many times it's going to recompute how much it's, I guess, kind of repelling itself internally, as well as other constraint types. But for our purposes, just really about stacking particles. I'm also going to increase the static threshold so that the particles are a little bit stickier when they collide with the ground. And you can see it's running a little bit slower, but the particles are no longer kind of moving as much once they hit the ground. They really are starting to make a stack, which is what we're after. Another thing that we could do is I just want to talk about real quick is like how I increase these constraint iterations on the solver, there's also a min and max substeps. Substepping in your simulation basically is doing it's how many times per frame the solver is going to recalculate what the positions of the particles. So generally speaking, more substeps equals a more accurate simulation at the expense of being a longer to compute simulation. Now up here on the AutoDOP network, there's also another substeps here. So there's actually a global substep that we can use to control how much this entire DOP network solves, how many times per step it solves. Now it's different because there's also one on the POP solver. And I find that generally speaking, it's better to set the substeps on your solver if you have the opportunity to, instead of out there on your DOP network. Just because it makes things, I find it gives a little bit more control and a little bit more performance since you're only substepping this solver and not everything in the scene. Or in the DOP network. So if I turn these substeps up to something like a minimum substep of 10 and a max substep of 10 and hit play, it's going to play back quite a bit more slow, but we would generally get much more accurate results. Now, being as this simulation is pretty basic, it's kind of a waste of resources at this point. So I'm going to turn it back down, but it's just important to note where your substep settings are. So bringing those back down to 1, we've got our constraint iterations up. So really constraint iterations and substeps are going to be what kind of control your the quality of like a grain sim or a vellum simulation. A lot of this constraint iteration stuff is pretty accurate or applicable to a vellum simulation, and which we will be covering at a later in a later section of this series. But so here we've got our particles kind of stacking up, so that's cool. Now I want to move away into trying to do something a little bit more abstract with this. So I'm going to actually ditch the floor. I'm going to turn this guy off. And what I want to do is maybe have these particles form in midair and then kind of suck into the center. So I'm actually going to bring them back to 0. So I'm just going to turn off this transform again. So now we're emitting from 0. And in fact, I don't really want this curve force to be visible anymore. So I'm going to go up to my object level and hide it. And then getting back into this DOPNet here, maybe what I want to do is throw down a pop attract. And if I throw it on the pop attract, by default, I'm going to just put it above the grain solver because these generally execute in order. And I want the grain solve to happen after the attraction. So now if I play this back, nothing's the objects are still falling because our gravity is still turned on. So I'm going to turn that off. So now if I play this back, you can see these the particles are being created, but they're also repelling each other once they're born. But then you can see that they're floating out and then they're being attracted back inwards towards this pop attract that we created. And you can see the pop attract, the goal of the pop attract is set to 0, 0, 0. If I were to change that to something like 0, 0, 3.40, so I've moved it up 3.4 on the y-axis, these particles are all going to sort of start being attracted up to that point. Like so. And then once they move past that point, they're going to start to kind of want to drift back down. I don't think that they actually live long enough to be able to do so because we had set our life to be something only like 5 seconds. But so you kind of get the idea. Now, I'm going to bring this attraction back down to 0 so that the goal is at 0. And I can mess around with the force here. I can just, if I increase this force scale, that attraction force will be much more drastic. And you can see it sucking these particles into the center of the scene very aggressively, and then creating like a little chunk there for us, which is kind of cool. I'm going to go up to the sphere source and turn off the guide, because I don't want to see that anymore. So if I click play, you can see it really kind of sucking all those particles in towards the center, and they're kind of just hovering around in there. Just kind of cool. But let's see. Suppose at this point, like I thought that maybe these particles are all kind of uniform in scale and it's kind of boring. So I could actually add some variation to that. So I'm going to do that by inheriting the P scale like we set over here. I can just add some more noise to that. So instead of having P scale is just being set to whatever this, I'm going to turn, let's see here. If I throw down a scatter after here, I can visualize this a little bit better. So if I just turn this down, you can see this P scale is in general roughly about this size. I want to add some variation to this. So I'm going to throw down another attribute noise. And instead of randomizing color, I'm just going to randomize a one-dimensional attribute called P scale. And now if I wire this in here, you can see I get all sorts of different P scale values. And here, if I just change that amplitude, you can see that it goes, they'll kind of go back down to normal. So what I could do here is I could click remap noise, and this would allow me to set a new minimum and maximum value. So maybe I want my minimum noise size, my minimum particle size to be 0.001 and my maximum to be 0.01. I should now have some randomness to it. I'm not really seeing that. Probably because I need to have a little bit more frequent of a noise, and it looks like this isn't, it's just not varying very much. Let's just increase here and maybe bring this down a little bit. Yeah. So now I've got some particles that are, you can see here, the values that I've created here for my P scale are really ranging from negative value, which is not what I want, up to 0.3. I think at this point, instead of using this attribute noise, I might just use an attribute VOP, just because I can be a little bit more, I can have a little bit more control over it. So I'm going to throw down an attribute VOP. And instead of wiring in this, I'm going to just bypass and go over here, and then I'll throw down my scatter and my sprite. Again, this scatter and sprite are just off to the side for visualization purposes. Maybe turn off relax iterations as well. So I also don't really need this display flag up here. I just am really concerned with the P scale of these points. Maybe going to scatter a few more points just to have something to look at there. I'm going to hit the pin key up here, and then I'm going to dive inside the attribute VOP. So inside here, I've got, I don't have a P scale attribute in my global, so I got to bind it in. So I'm going to bind in my P scale. So P scale. And I'm going to just bind export. I'm going to bind export this to P scale as well. So I bring in P scale, which we have set. I'm going to export it to P scale. So now if I were to bring in a noise, I'll do a anti-alias noise. I'm going to use the position to look up the noise, and I'm going to just wire this noise into the export. You can see that it is creating all these different varying sizes for us, which is cool. Now if I look in my P scale attribute, I am getting values that go from positive 0.3 to negative 0.3. So I'm going to need to remap this to be from, in a positive range. So I'm going to go throw down a fit, and I'm going to put in, let's see, instead of doing a, let's see, it looks like we've got the source min from 0 to 1. I want the source to go from negative 0.3 to positive 0.3. And now, so because I had values going from negative 0.3 to positive 0.3 in this p-scale value, now I can remap these to be from some very tiny value to a slightly larger value. So let's just bring this destination min up to maybe 0.001, like so, and then the max will be something like that. So now I've got particles of varying sizes on my surface here. And, really at this point, I didn't need to actually bind. I didn't need to import my p-scale because I'm just creating it here. So I can actually delete this. If I'm just binding this out, I can just leave it. I can just create it in this VOP. This VOP is actually what is creating our p-scale attribute. And we don't even need this attribute create anymore. So I can just delete that. And I'll just delete this noise as well. Because basically, I took those two nodes and made my own version of it using this attribute VOP, which is kind of cool. So now, if I were to go into my PopNet, I'm going to unpin this so I can see what's going on in here. I jump inside here and click play. You can see I've got different sized spheres all starting to collide with one another, which is cool. So now let's see if I go, I'm going to just increase the birth rate to something like 200. And maybe I want these to kind of grow out of the middle. So actually I'm going to go up to my sphere here, and over here where this attribute VOP is being created afterwards, I'm going to throw down a transform just to make this a little bit smaller, but retain the same noise pattern that I had before. So I'm just going to bring this down to something like 0.1 instead. So now all of our particles should be sort of growing from this central area and kind of bursting outward, which is great. That's kind of what I'm after. Maybe I'll actually increase the range of these points as well, the p-scale points. So I'm actually going to go up here, and maybe I'll promote the destination min and destination max value on my fit range. So the way I'm doing that is just middle mouse clicking on here and clicking promote parameter. So now I've got these two parameters up here on my attribute VOP. So I can just dial this in up here. So I'm going to go pretty extreme with this maximum value. And I'm just going to dive back in here and see what that gets us. This should just blow up now, which is kind of cool. So maybe at this point, what I want to do is I want to have this simulation run for like maybe a second. Have a burst of particles come flying out, and then I want it to, them to kind of like disappear or die. So I've got my, I've got my my life expectancy is 5. My life variance is 2.5. So, this is great. My particles are being created, but one thing I'm noticing is that they actually are, they're just like, when they're spawned, they just pop into place. They appear instantaneously at their p-scale. So what if I wanted these to grow into position first, and then what if I wanted these to grow into position first, and then actually shrink and die away at the end of the simulation? What I could do is actually use a similar situation inside of POPs. So one of the most powerful nodes in SOPs is the attribute VOP, and we have that inside of POPs. So this is super cool. Let's throw one down. So right after this pop attract, I'm going to throw down a pop VOP. So a pop VOP is just like an attribute VOP, except now we have this sort of control inside of our scene. And now one of the cool things that's created by our pop source is we've got a life expectancy and a life variance. And if you look at our attributes down here, again in pop object, go to geometry, you can see we have an age. So we have a particle age, and we also have, if I go under view, I'm going to say hide all attributes and say show age and life. So I've got particles that are, I have their age and their life expectancy. So with this, I can actually calculate the percentage of the age of these particles. And if I know because I just divide the age by the life, that percentage will give me a value from 0 to 1. And values from 0 to 1 can easily be plugged into ramps and then refed back into the particle system. So let's create a ramp based off of the age of our particles, so they can grow into position and then eventually shrink away and die, and behave correctly according to dynamics all along the way. So I'm going to just throw down I'm going to dive inside the pop-up, and I have got these attributes right here. You can see age and life are available already in the globals. So all I need to do is get a divide. If I get a divide, and I bring these two in, and if I just bind these two values out to p-scale, I'll say bind export to our attribute p-scale. You can see that I'm just going to also scope p-scale into our geometry spreadsheet by going under view now and selecting p-scale. So now what the particles are going to do is they're actually going to grow from 0 up to a p-scale of 1 until the moment that they die. And you can see that this is happening. So as their age increases, if I sort by age, you see that as their age approaches their life. So for example, this first one, its age is 1.9 seconds and its life is 6.6. Its life expectancy is 6.6 seconds. And you can see that its p-scale is just a percentage of that. So by the time we get all the way out to the end of this simulation and these particles start dying, these have reached a p-scale of 1. And if you look at our grid, this is the size of 1 unit right here. So that makes sense. These particles are growing from a size of 0 up to a size of 1 and then immediately dying. Now, we want to actually use the original p-scale that we used in this simulation. So we could actually multiply that p-scale by a ramp. So I'm going to just take this divide, and we're going to throw down a ramp. With this ramp, we're going to use a spline ramp. And it goes to, nothing shows up. I'm going to go back to 0. I'm going to hop up out of our network here onto the pop-up, and you can see that they've got, it's just a ramp set to nothing. I'm just going to increase it so that it actually increases in size and then shrinks away towards the end. And maybe I'll do something like that. So now these particles should grow and then eventually start shrinking as they get older and older and older. Which they are, which is cool. So as they get older and they're getting sucked in, they're shrinking. That's great. I'm actually going to, let's just go up here into our sphere source. I'm just going to have this impulse activation stop, or I'm going to have the constant activation stop after 1 second. So I'm going to just, I'm going to right click and delete the channels here. And I'm going to set a key here by option clicking in that parameter, or alt clicking in that parameter, moving forward to frame 25 and just setting this to 0 and then alt clicking again. So now we should just get a burst of particles that come out and then they stop, and that attractor starts pulling them in and they start bouncing off each other until they all eventually die. I'm also going to maybe decrease the life expectancy of these particles a little bit and maybe move the variance down to 0 just to make things a little bit easier for the time being. So I'll change the life expectancy to 2. So now they pop out, increase in size, and they start getting sucked back into the center. Fun. So really what the scale of these particles is doing is they're behaving according to this ramp that we're using to drive them. And it's just solving that for every single frame, which is really cool. It's just coming up with that value based off of the percentage of how old it is versus how long it's going to live. So these are all really fun things that we can do with pops. Now, I know that this is sort of like all over the place, but I just think it's cool to kind of, you know, it's a playground, you know, we got to just go through this stuff and kind of just see what some of the possibilities are. And obviously we barely even scratched the surface with pops. I mean, we have all these other types of setups. We could throw down drag, just to get things to like move a little bit slower. If you want them to like behave in a more kind of predictable and controlled way, you can throw down a bunch of air resistance to get them to act nicely. And sometimes that helps your simulation. I don't know if it's necessarily helping this one at all. They're actually slowing down quite a bit towards the end, but you've got drag forces, you've got wind forces, there's all sorts of things. I definitely encourage you to just have an experiment with some of these, see what you can get them to do. So that was a general overview of, what particle, sort of DOP theory, particle theory. It sounds like we're talking about like physics or something like that. But I mean, well, it is kind of like physics, but really it's not quite as in depth as some of that stuff. But I felt that particles was a good way to kind of just like experiment and kind of introduce the DOP context to you. So now in the next example, what we're going to do is we're going to take all these kind of concepts that we did and we're going to apply them to a project that looks nice and pretty. And so we've got goals, and we can kind of like see what these particles look like when we're actually producing something that has a decent result in the end. So stay tuned for that lesson, and I'll catch you over there.